while they're getting set up, we're very excited to have a team from the University of Illinois at Urbana-Champaign. They've been one of our premier FreeFlyer University users for multiple years now. FreeFlyer University is a great program where FreeFlyer is available at no cost to university students and professors around the world for most reasons. If you're using FreeFlyer in class, or if you're using FreeFlyer for projects, or even for unfunded research, we're happy to be your partner in providing FreeFlyer. And with that, let me throw it over to Michael at the University of Illinois Urbana-Champaign. Michael, can you hear us?
Yes, sir. Thank you for having me.
No problem. Take it away.
So this is Michael Lembeck. I'm the director of the Laboratory for Advanced Space Systems in Illinois, and I just wanted to give a little introduction prior to Michael starting. We've been using FreeFlyer now for the last 3 years in both our classes and research. And today we'd like to talk to you about one of our prime uses of it that is rather unique in a hardware in the loop test system that Michelle Zowski has been working on. And she's a little under the weather today, so Michael's given the presentation, but she's online and available to answer questions. We're also going to talk about very briefly about 2 other applications we're doing just to show the versatility of how we're using it. And with that, I'll shut up and let Michael talk about hardware in the loop small satellite test applications.
Thank you, Professor. Hi, my name is Michael Harrigan. Today, I'm going to show you how our laboratory uses FreeFlyer for small satellite development. So, small satellites historically have a higher failure rate than desired, in large part due to inadequate testing. Hardware testing is pretty simple. Do you see a signal on one end when you put a signal in the other? The hardware validation testing is very simple, but flight software, on the other hand, can be a little bit more difficult, especially testing realistic mission parameters. Here's one example scenario. If you have a thruster, 2 thrusters trying to spin up a small satellite, you can't really test that in the same way. When they fire in opposite directions, it's going to create a torque, which results in the spin up of a satellite. The gyroscope inside the satellite will measure the spin rate and, using the flight software, control the thrust. When the desired rate is achieved, the thruster will stop firing. Hardware in the loop seeks to simulate this. To improve on-orbit viability, using hardware in the loop simulation can help validate software. In this example, the thrusters are an input to the system, measured to get integrated rates. The loop then closes by feeding the flight computer the new generated dynamic data. FreeFlyer is a tool that we use to help with this hardware in the loop testing. FreeFlyer provides the capability to simulate orbital mechanics for a satellite while allowing for communication interfaces from external hardware. Programmable runtime scripts also allow for the modeling of spacecraft dynamics. In this case, instead of using an actual flight computer, we can use a Raspberry Pi to emulate the satellite flight computer. The Raspberry Pi is responsible for emulating sensors and calculating the proper control algorithms using Python. A JSON file is then passed from the flight computer to FreeFlyer, where the dynamics are calculated, and then this JSON file is passed back to the flight computer. Here you can see an example configuration for how to configure the socket, which allows for communication between the Raspberry Pi and FreeFlyer. We set FreeFlyer as the socket server. One important note is that the FreeFlyer computer and the flight computer need to be on the same network. Here is an example of the Python script we would run on the Raspberry Pi. Here we are connecting directly to the FreeFlyer computer. This is an example of the JSON output that FreeFlyer is sending to the flight computer. It's going to take all the orbital calculations simulated and pass back the simulated satellite attitude. This is an example of how FreeFlyer is parsing the JSON file that is then passed from the flight computer to FreeFlyer. It reports the outputs from the onboard components, such as sensors and actuators, so that FreeFlyer can properly model the dynamics. On the FreeFlyer side of things, an RK4 routine is used to integrate the satellite's rotation rates, attitude quintillions, and command torques. On the Raspberry Pi side, the flight models and algorithms are used to accurately model the results of different inputs. Body dynamics, one of the significant challenges that we encounter is that body dynamics like to be modeled on the order of tens of milliseconds to maintain numerical accuracy, while the orbital dynamics can be integrated on a much larger time step. Finding a balance between these two is one of the challenges we encounter. Another challenge is that any delays introduced by dynamics simulation can affect the stability of control loops using the computation results as an input. One solution to this is using faster computers and hand optimizing code to minimize this delay. Our vision for a hardware-in-the-loop test involves FreeFlyer-based hardware-in-the-loop and will enable small satellite integration and testing to verify and validate mission performance across the entire mission regimen. This includes orbital mechanics, attitude determination and control, satellite inertial configuration changes mid-flight, and primary payload simulation. I'm going to go over now some of the other applications we have for FreeFlyer here at the university. We used it primarily on two other projects. One is a dark matter detection satellite that would operate in low Earth orbit using an X-ray sensor to search for dark matter particle decay signals. The other is an atmospheric gravity wave detector satellite in low Earth orbit for improved weather prediction capabilities. Here in the dark matter example, FreeFlyer was used to determine the effects of RAN on Earth's obstruction of the payload's field of view in what we call a molar chart. In this example, the blue region of the chart is an acceptable field of view, while the gray version of the chart is an unacceptable field of view. FreeFlyer sensor objects are used to compose a custom procedure that records the time that the sensor's FOV is obstructed, while the satellite traverses through umbra and points the payload sensor towards dark matter sources. Another example is our atmospheric gravity wave detector satellite. In this case, FreeFlyer is used to provide a list of available communication opportunities for downlinking the scientific data. Knowing the longest period of time between passes, mission designers are able to size the mandatory data memory buffer and determine the required radio bandwidth to meet mission objectives. In conclusion, FreeFlyer is a very versatile tool. It's extremely extensive and has great orbital mechanics and dynamics simulation. The user interfaces for quick socket connections to external hardware allow us to facilitate our hardware in the loop testing. The scripting language is extremely easy to learn and extremely powerful when applied to small satellite simulations. And without FreeFlyer as a tool, hardware in the loop testing would not be enhanced nearly as much as it is, or even feasible. UIUC would like to acknowledge AI Solutions for supporting our aerospace undergraduate education and graduate research projects. Thank you.
Excellent. Thanks very much, Michael. We do have some time for some questions, so let me just get those pulled up.
All right.
First question for you. Is the torque integration done inside of FreeFlyer? And if yes, how is that done? Is it scripted, or is there an extension?
This is Michelle. The torque integration is done inside of FreeFlyer in a script. So it's in the RK4 integrator that takes in that torque from the Raspberry Pi and does that integration there and applies it to the simulated satellite.
Gotcha. So the RK4 is on the script level.
Yes.
Great. Do you have, if we could stay on the screen for a second, are there outputs that you use in FreeFlyer to verify that the system is working as expected?
We have the command quaternion and then the actual quaternion that the satellite is experiencing in FreeFlyer to verify once the torque is applied that the satellite is in fact at the desired quaternion, that it lines up. And we use a similar process to verify our attitude determination, which is happening on the Raspberry Pi side. We're sending the determined attitude over to FreeFlyer to compare with the actual attitude to make sure our determination algorithm is accurate enough. I'm sorry,
Great.
I don't have those plots ready to show right now, but that's how we're doing the verification.
No, it's all good. Thanks for explaining that for us. I think the only other question that I have here is, I guess one more question. Have you all looked into using the runtime API in addition to the socket?
Yes, I think we ran into some issues with the runtime API. Is that only available for the mission tier?
Yes, runtime available API is for the mission tier. We can get that to you guys if you're interested. For everyone, FreeFlyer has two tiers, engineer and mission. for our university program, we start everyone off with engineer. If you have a use case that makes sense for you to use FreeFlyer mission for the university use case, just let us know. We're happy to upgrade you to mission tier as needed. So for instance, the optimization and the OD features that we added for this release are only in the mission tier. So if you need that for school, let us know. We're happy to get you an upgraded license with more of those features.
Yeah, that'd be great.
Yeah,
Thank
for
you.
sure. We certainly appreciate it.
Awesome. I think one more question that the FreeFlyer team asked me to ask you guys is, what are some things about FreeFlyer that have made this project and some of the other projects that you spoke about better or easier? And what are some key features that we should add to make it even better?
I personally really enjoy the scripting capabilities. I really feel like between that and some fancy vector work, I can basically simulate almost any scenario I want. Anything from ground passes to power calculations. I really feel like I can simulate nearly the entire body through FreeFlyer at this point. The only areas that we aren't able to simulate currently is thermal level. So adding some features that would allow for that capability would be my biggest recommendation.
Yeah, I can say as a longtime Visual Basic programmer, the scripting language is very convenient and intuitive to use. We have found that we start thinking about problems here and we look for alternate solutions. Wait a minute, can we do that in FreeFlyer? And most often the answer is yes, because of the ability to script and run code that we've had elsewhere that we can re-internalize it as a script and keep it running dynamically. And as you know, as a hardware in the loop capability, being able to have that external interface to be able to send data back and forth and basically operate with two different time steps. That's key to us. We have to, run the dynamics very quickly on the order of 40, 50 milliseconds, while the orbital mechanics can run at a separate pace. So I don't know how to explain this cogently, but something akin to a thread system where you could run one set of code at one rate and a second set, like the orbital mechanics, in a separate thread would be a good utility to have.
A different interrupt speed per se.
Yeah, that makes a lot of sense, and something we'll definitely take into consideration. So thanks for that. If you are listening in the audience and you have other ideas for things that we should add to FreeFlyer, please give those to us in the chat, and either foot stomp what UIUC has said, or give us any other additional feedback. Well, thanks, Michael and Dr. Lindbeck and Michelle for a great panel. What we're going to do now is take a brief break. We will start at the top of the hour again with Luke Schoenwetter presenting to us on FreeFlyer optimal control continuous thrust GTO to GO. Thanks very much, everyone.
Thank you very much for your time.